In our previous lectures, we learned a lot about time complexity of loops. Now from this presentation onwards, we will solve problems based on time complexity of loops. In this presentation, we will solve problem number 1. So let's get started and let's see the topics. The topic is time complexity of loops solved problem. Let's proceed and let's see the problem first. Here is the problem. Consider the following C program fragment in which I, j and n are integer variables. Here is the C program fragment, and precisely this is the for loop in C where I is initialized to n, j is initialized to 0, I is compared with 0. If I is greater than 0, then I is updated to I divided by 2 and j is updated to j plus I. Let val j denotes the value stored in the variable j after termination of the for loop. Which one of the following is true? These are the options given to us, and our job is to determine the correct option. Is val j equal to theta of log n? Is val j equal to theta of square root of n? Is it theta of n or is it theta of n log n? Let's try to find the correct option out of these options. We need to find the value of j in terms of asymptotic notation, as it is mentioned in these options. Val j represents the value of j after termination of the for loop. We now need to find the value of j after termination of this for loop. Let's try to solve this problem. We know at this point val j represents value of j after the termination of the for loop. Now we want to find val j. In order to find val j, we need to analyze each iteration of this for loop. And for each iteration, we need to carefully observe different values of I and j. In the iteration number 1, I is n and j is 0 because I is initialized to n and j is initialized to 0. So one thing is clear, in the iteration number 1, I is n and j is 0. Then after this, I is compared with 0. I is equal to n, so this I will be replaced by n. Is n greater than 0? Let's say n is greater than 0, so the condition is satisfied. Hence, this statement will execute. I divide equal to 2. I is updated to I divide by 2. What is the current value of I? I is n. N is divided by 2, so we will get n by 2 in the variable I. And then j is updated to j plus I. The current value of j is 0 and the current value of I is n by 2. Remember, because of this statement, I is now holding value n by 2. So after execution of this statement, the value of j will be n by 2 because 0 plus n by 2 is n by 2. So in the iteration number 2, the value of I is n by 2 and the value of j is also n by 2. Now what happens after this? I is again compared with 0. Let's say n by 2 is greater than 0. This condition is satisfied, therefore this statement will execute. I is updated to I divide by 2. The current value of I is n by 2 and n by 2 now needs to be divided by 2. After division, we will get n by 2 square. So this will be the new value of I. Now what happens to j? J is updated to j plus I. We know the current value of I is n by 2 square and the current value of j is n by 2. N by 2 square is now added to n by 2 and this is the new value obtained in variable j. So in the iteration number 3, I is n by 2 square and j is n by 2 plus n by 2 square. After this, again I is compared with 0. Is n by 2 square greater than 0? Let's say n by 2 square is greater than 0. Condition is satisfied. Therefore, I is updated to I divide by 2. This means I becomes n by 2 cube. And what about j? J is updated to j plus I. The current value of I is n by 2 cube and the current value of j is n by 2 plus n by 2 square. So the new value of j will be n by 2 plus n by 2 square plus n by 2 cube. So in iteration number 4, the value of I is n by 2 cube and the value of j is n by 2 plus n by 2 square plus n by 2 cube. At this point, we can observe a pattern. The value of j in iteration number 4 is n by 2 plus n by 2 square plus n by 2 cube. We can observe the difference of the powers of 2 is 1. We have 1 here in the first term as the power of 2. In the second term, the power of 2 is 2. In the third term, the power of 2 is 3. Also, we can observe that the power of 2 in the last term depends on the iteration number. It is always 1 less than the iteration number. Here we have 3 because the iteration number is 4. Here we have 2 because the iteration number is 3. Here we have 1 as the power of 2 because the iteration number is 2. Similarly, if let's say this loop executes k times, then in the iteration number k, the last term will be n by 2 power k minus 1. And in the iteration number k, value of j is val j. This means it represents value of j after the termination of the for loop. Why is that the case? I'm assuming that iteration number k is the last iteration of this for loop. This means in the iteration number k, the value of I represents the last value of I for which this condition is true. After this, the loop will terminate. Therefore, the value of j obtained in the iteration number k represents val j. This means value of j after the termination of the for loop. So, it is clear that val j is equal to n plus n by 2 plus n by 2 square plus n by 2 power 3, and this will continue up to n by 2 power k minus 1 because the iteration k is the last iteration of this for loop. This is my assumption. Now let's represent value of k in terms of n. We also observe in the pattern that the last term of j in each iteration is equal to the value of I. If the value of I in some iteration is n by 2 square, then the last term of j will be n by 2 square. If at some point the value of I is n by 2 cube, then the last term of j will be n by 2 cube. This is what we observed in the pattern. In this value of j, the last term is n by 2 power k minus 1. This is the value of j in the kth iteration, and the last term of this value is n by 2 power k minus 1. So clearly, I is also n by 2 power k minus 1. So now we know what is the value of I in the kth iteration. Let's assume this value of I is equal to 1. Because for I equal to 1, the condition is true, but for I equal to 0, the condition fails. I'm assuming that the kth iteration is the last iteration. And hence I'm assuming n by 2 power k minus 1, which is the last value of I, is equal to 1. Because this represents the last value of I for which I is greater than 0. So this is my assumption that n by 2 power k minus 1 is equal to 1. Now let's solve this equation to find the value of k in terms of n. We will get 2 power k minus 1 equal to n from this equation. And now we can apply logarithm on both sides. This will bring k minus 1 to the base. As we want to find the value of k, we need to bring k minus 1 to the base. This is the reason I am applying log on both sides. Let's apply log base 2 on both sides because here we have the constant 2, and after applying log base 2, we will get 1 as the result for log 2 base 2. So after applying log on both sides, we will get log 2 power k minus 1 base 2 in the LHS and log n base 2 in the RHS. Now we can solve this equation. Here we have log 2 power k minus 1 base 2. We know the property of logarithm. Log a power b base c is equal to b times log a base c. So in the LHS, we will get k minus 1 times log 2 base 2. And in the RHS, we are having log n base 2. So this is equal to k minus 1 equal to log n base 2. Because log 2 base 2 is 1, we are getting k minus 1 here in the LHS. Because k minus 1 times 1 is k minus 1. And in the RHS, we have log n base 2. And this implies k is equal to log n base 2 plus 1. We can add 1 on both sides. This will remove minus 1 from the LHS. And after adding 1 on the RHS, we will get log n base 2 plus 1 in the RHS. So k is equal to log n base 2 plus 1. So this is the value of k in terms of n. Now we can replace k by log n base 2 plus 1 and we will get 2 power log n base 2 in the denominator of the last term. So val j is n plus n by 2 plus n by 2 square plus n by 2 cube and so on up to n by 2 power log n base 2. Now we can take n common and we will get n times 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube, and this will continue up to 1 by 2 power log n base 2. This is the GP series or geometric progression series. Why am I saying this is GP series? Let's recall what is GP series and how to find the sum of all these terms. In a geometric progression, each term is obtained by multiplying the previous term by a constant. So, each term of a geometric progression is obtained by multiplying the previous term by some constant. For example, this is the geometric progression because each term of this geometric progression is obtained by multiplying the previous term by a constant. 2 is obtained after multiplying the previous term, which is 1, by a constant. In this case, the constant is 2. If we multiply 1 by 2, we will get 2 as the result, which is the second term of this geometric progression. Similarly, the third term, which is 4, is obtained after multiplying 2 by 2. After multiplying 2 by 2, we will get 4 as the result. Similarly, 8 is obtained after multiplying 4 by 2. 16 is obtained after multiplying 8 by 2. So this is the geometric progression because each term of this progression is obtained by multiplying the previous term by a constant. Now let's discuss the general form of the geometric progression. The general form is a, ar, ar square, ar cube, and so on, where a represents the first term and r represents the common ratio. The constant that we considered in this example is the common ratio. The first term in this example is 1. So a in this example is 1 and r is 2. If we multiply 1 by 2, we will get 2 as the result, which represents the second term. So the second term is AR because it is obtained after multiplying A by R. Similarly, the third term is AR square because it is obtained after multiplying AR, which is the second term, by the common ratio R. AR times R is equal to AR square. So AR square is the third term of the geometric progression. Similarly, the fourth term is AR cube because it is obtained after multiplying AR square by R. In this example, The fourth term is 8. It is obtained after multiplying 4 by 2. 2 is r and ar square is 4. So clearly ar cube is equal to 8. In this way, we can form the geometric progression. Now we know what is geometric progression and what is its general form. Let's now learn how to find the sum of geometric progression. The sum of n terms of geometric progression is equal to a plus ar square plus ar cube and so on up to ar to the power n minus 1. There are a total of n terms in this geometric progression, and this sum is equal to a times 1 minus r power n divided by 1 minus r. This is the formula to calculate the sum of n terms of the geometric progression. So, in order to calculate the sum, we need to know what is n, what is r, and what is a. Now our job is to find the sum of this series. And we know this is a GP series because each term is obtained after multiplying the previous term by a constant. In this case, the constant is 1 by 2. So r is 1 by 2. And what is a? A is 1. This is the first term of this series. And r is 1 by 2. So if we multiply 1 by 2, we will get the second term, which is 1 by 2. In order to obtain the third term, we need to multiply the second term, which is 1 by 2 by 1 by 2. We will get 1 by 2 square. The third term is obtained after multiplying the second term by the common ratio, which is 1 by 2. So we will get 1 by 2 cube as the result of the third term. In the same way, we can obtain the rest of the terms as well. So clearly this is the GP series. And now we want to calculate the sum of this GP series. How do we do this? We know the formula. The sum of n terms of the GP series is a times 1 minus r power n divided by 1 minus r. What is a? A is 1. What is r? R is 1 by 2. And what is n? N is log n base 2 plus 1. Why? Here we can observe in the last term we have 1 by 2 power log n base 2. We can observe the first term is 1 by 2 power 0. The second term is 1 by 2 power 1. The third term is 1 by 2 power 2. The fourth term is 1 by 2 power 3. So in the powers of 2, the difference is always 1. And as the first term is 1 by 2 power 0, there are a total of log n base 2 plus 1 terms. As in the last term, the power of 2 is log n base 2. If the first term starts with 1 by 2, then there are a total of log n base 2 terms. But here, the first term is 1, which is 1 by 2 power 0. So clearly there are log n base 2 plus 1 terms in this series. So one thing is clear, that n is equal to log n base 2 plus 1. So this sum is equal to 1 times 1 minus 1 by 2 power log n base 2 plus 1 divided by 1 minus 1 by 2. And as we have n here, so sum is multiplied to n, we will get n times 1 minus 1 by 2 power log n base 2 plus 1 divide by 1 minus 1 by 2. Now 1 minus 1 by 2 can be rewritten as 1 by 2 and we can bring 2 here, so we will get 2n times 1 minus 1 by 2 power log n base 2 plus 1. 1 by 2 power log n base 2 plus 1 can be rewritten as 1 by 2 power log n base 2 times 1 by 2. And what is 2 power log n base 2? 2 power log n base 2 can be rewritten as n power log 2 base 2. Why? This is also one property of logarithm. A power log b base c is same as b power log a base c. So we can rewrite this fraction as 1 by n power log 2 base 2. What is log 2 base 2? Log 2 base 2 is 1, because we know log a base a is 1. So this fraction is equivalent to 1 by n. We are getting 1 by n times 1 by 2 here. 1 by n times 1 by 2 is 1 by 2n. And what is 1 minus 1 by 2n? This can be rewritten as 2n minus 1 by 2n. After taking LCM, we will get 2n minus 1 by 2n as the result. Now we can observe we have 2n here and we have 2n in the denominator as well. We can cancel these two terms. And now we are getting 2n minus 1 as the result of val j. So val j is equal to 2n minus 1. This is the value of j after the termination of the for loop. But recall in the options, we need to represent val j in terms of asymptotic notation. 2n minus 1 can be written as theta of n, because 2n is the dominating term, and we can eliminate this constant also. So we are left with n. So 2n minus 1 is theta of n. So theta of n is the value of j after the termination of the for loop, and hence option C is the correct option. So with this, we are done with this topic, time complexity of loops, solved problem, and this means we are done with this presentation. Okay friends, this is it for now. Thank you for watching this presentation. I will see you in the next one.